Our first video for Chapter 8 about interval estimates, or as I will usually call them, confidence intervals. So in the last chapter, we were using sample data to find point estimates for different population parameters. But a point estimate can take on many different values depending on the actual sample that was selected. So we need to have some measure of how good our point estimate actually is. What we do instead of just looking at the point estimate is that we construct a whole interval, a range of values that we think estimates the true value of the population parameter. The confidence level of our interval tells us the probability that the estimate actually includes the true population parameter. So we're going to start out here with estimating a population mean. We've already seen that the sample mean, x bar, is the best point estimate of our population mean, mu. And again, since the sample mean is going to vary depending on which sample we actually selected, we're going to construct a confidence interval that gives us a whole range of values for our estimate of mu. The sample mean will be in the center of the interval that we end up with, and the distance that the interval spreads out on either side of the sample mean is called the margin of error. Here's an example. A national education organization wants to estimate the average IQ score by state for high school students across the country. They plan to select simple random samples of 75 students from each state and administer the IQ tests. So the point estimates will be the sample means for each of the 50 samples. However, they want to avoid the possibility of complaints. For example, if one state's sample mean score is especially low, they may say it was low because a bad sample was chosen. So the mean IQ scores are also going to be estimated using confidence intervals. The organization wants there to be a 95% probability that each interval includes the actual population mean of the IQ scores for that state. Samples were selected from each state and the results were calculated. Here's one of the sample results. From this sample, we got a sample mean of 103.0 for the IQ, and developed a confidence interval around that sample mean that goes from 99.6 to 106.4. Here's what it would look like if we graphed this confidence interval on a number line. Notice that right in the middle of the interval is our sample mean of 103.0. That's our point estimate. And then if we look at the distance on either side from that sample mean to the endpoint of the interval, that is actually our margin of error. So from the sample mean, we're going down and up by the margin of error to get our two endpoints for our confidence interval. Now, what about the 95% probability that we wanted, the confidence level? This is actually one of the things we use in a formula that you'll see later to find the two endpoints of the confidence interval. If we have a confidence level of 95%, that means if we selected 100 different samples and calculated confidence intervals for each one, approximately 95 of them would include the actual population mean. So 95 out of the 100 confidence intervals would be hits, and the other 5 would be misses. For example, if the population mean is actually 102, approximately 95 of the 100 confidence intervals would include the value of 102. Those would be the hits. And approximately 5 of the intervals would not include the value 102. Those would be the misses. We're going to look at 3 more samples, and if we assume that the population mean is actually 102.0, here's our second sample. Notice that we have the confidence interval and 102.0 is actually in that interval, so that one's a hit. Sample 3, the population mean is close to the end of the interval, but it's still between the two endpoints. So that one's also a hit. In sample 4, notice the interval doesn't cover the 102.0, so this one would be a miss. Now, if we're actually going to construct the confidence interval, we need to know something about how we're doing it. In this video, we're just going to talk about estimating a population mean if we know the value of the population standard deviation. So the requirements to be able to do this: number 1, the sample that we select has to be a simple random sample. So all samples of the same size have an equal chance of being selected. We have to know the value of the population standard deviation, sigma, and we have to have one or both of these conditions satisfied. that either the original population is normally distributed or that n, our sample size, is greater than 30. And here are all the different symbols we'll be using. Mu stands for the population mean, sigma stands for the population standard deviation, n is the sample size, E is going to stand for our margin of error, alpha is going to be the area in two tails of the standard normal distribution, and that has to do with our confidence level. And z of alpha over 2 is the z-score that we'll find that separates an area of alpha divided by 2 in the right tail of the standard normal distribution. And this z-score is called a critical value. Here are some of the formulas that we'll use. For the margin of error, we're going to take z of alpha over 2 times sigma divided by the square root of n. And remember in this case that sigma has to be our population standard deviation. To get our confidence interval, we need those two endpoints. So the lower endpoint, or the lower bound, is going to be our sample mean minus our margin of error. Upper endpoint, or the upper bound, is going to be the sample mean plus the margin of error. Now, how to find our critical value? First of all, we have to find alpha. So we start with our confidence level, we convert that to decimal form, and then we subtract it from 1 to get alpha. So here's an example of how we would find z of alpha over 2 with a confidence level of 95%. We convert the 95% to decimal form and then subtract that from 1. So we end up with alpha equals 0.05. Then the next step is the easiest one. We just take the alpha that we found and divide it by 2. So for this example, alpha over 2 is 0.025. Now we're going to consider alpha over 2 as a probability, and we need to find the z-score that corresponds to it. The way I'm going to show you, we will come out with a negative number for our z-score. So if you're using your calculator, all you have to do is use the inverse norm function, put in the 0.025 and 0 and 1 because we're looking at a standard normal distribution, and you should get negative 1.95996. If you're using the z-scores table, look up 0.0250 in the middle of the table, find the value closest to it, and its corresponding z-score should be negative 1.96. Now all we have to do is take the value that we found in the last step and change it to a positive value, and that's our critical value. So our critical value, z of alpha over 2, is going to be 1.96. So now we're ready to actually construct a confidence interval. Here are the steps that you have to go through. First, verify that those requirements are all satisfied. In this case, we need to verify that we had a simple random sample and that either the population is normally distributed or that our sample size is greater than 30. The next step is to find the point estimate, which is the sample mean, and we would find our critical value that corresponds to the confidence level we want. We would use those values to find our margin of error. Once we have our margin of error, then we find the sample mean minus the margin of error and the sample mean plus the margin of error to get our limits for our confidence interval. And finally, we can write our confidence interval in one of two ways. We can either write it as an inequality or we can write it in interval form. And the round-off rule, or mean, is that if we have the original set of data, then we're going to round the confidence interval limits to one more decimal place than what was used in our original set of data. If we don't have that original data, but we only have summary statistics from the sample, then we'll round the confidence interval limits to the same number of decimal places used for the sample mean. Here's an example of finding a confidence interval. The organization wants 95% confidence intervals that estimate the population means of the IQ scores. To do this problem, we're going to assume that we know the population standard deviation of IQ scores is sigma equals 15. The sample sizes we already decided would be 75. From the first sample, we saw that a sample mean of x bar equals 103.0 has been calculated. Our first question is, are all the requirements met? We were selecting simple random samples, we know our population standard deviation, and our sample size is greater than 30. We already have our sample mean for step 2, and we already found that our critical value for this problem is 1.96. So here's the formula that we're using. And if we calculate that out, we get 3.39482. Now we're going to find the two limits for the confidence interval. So we take that margin of error and first subtract it from our sample mean. Then we're going to round that to 1 decimal place, so we get 99.6. And then we go the other direction. We add the margin of error to our sample mean and round that to 1 decimal place, so we get 106.4. So we can write the confidence interval this way with an inequality or in interval form. Here's one for you to try. Okay, here are the solutions. Looking at our confidence interval, notice that 166.3 is in between those two values, although it's at the lower end of that confidence interval. So we could still use that mean weight. It could still be the correct population mean. However, since our point estimate was 172.55, that does suggest that the mean weight might have increased. Since this is an important safety factor, so that we don't overload boats or aircraft, an underestimate would be a serious problem. So the results suggest that we should do additional studies. And actually additional studies have been done. The mean weight of men that's used to determine safe capacities has been increased. Now, what if we have a confidence interval and we want to back up and find out the sample mean and the margin of error that were used? This isn't very hard. The sample mean we know is right in the middle of the confidence interval, so it's actually the average of the upper limit and the lower limit. So we can just add them together and divide by 2. Then the margin of error is just half of the distance of the whole confidence interval. So we can subtract one limit from the other and divide by 2 to get our margin of error. So for example, if we have this confidence interval from 457.9 to 502.3, for our sample mean, we would add those two together and divide by 2 to get 480.1. And our margin of error, we would subtract those two and divide by 2 to get 22.2. One last thing that we want to do, if we're starting to design a survey or a study, we can decide in advance what confidence level we want and what margin of error we would like to have. With these two pieces of information, we can determine the minimum sample size that we need. Here's the formula to do this. What we're doing in this case is finding n, so this is before we've actually done the survey or the study. We take the confidence level and find z of alpha over 2. This again assumes that we know the population standard deviation, so sigma is in the formula. And on the bottom is e, the margin of error that we want to have. One important thing to notice here is that this formula doesn't use the population size at all. This is actually a very misleading concept in statistics, and that is that a sample can be valid even if its size is very small in comparison to the population size. The validity of sample statistics doesn't depend on the population size. Here's an example of finding a minimum sample size. Going back to the IQ scores, suppose that the organization still wants 95% confidence intervals, but they've decided they want the margin of error to be only 2 points. They need to know what the minimum sample size should be. We already know that our critical value is 1.96, so if we put the values into our formula, we get 96.04. When we're determining a minimum sample sizes, we always want to round up to the next biggest integer. So the minimum sample size they would need to get this margin of error is 97.